We will wait one more minute and get started. Hope you can see my screen and hear me clearly. If not, please let me know on chat. Great. Okay then, let's get started. Welcome to the week 3 live session of the GPU Architectures and Programming course. Good evening to all of you, and hope you are making good progress with the course. We will go through some more problems today and address some doubts from the previous session as usual. So I hope that all of you have joined these sessions before, so you're kind of familiar with what goes on. But if not, this will be a 2-hour session, 7 to 9 p.m. and you'll have a 5-minute break in between. Around 8 p.m. I'll make sure that you get a 5-minute break, and we'll mostly focus on problem solving, and we'll be working on problems very similar to your assignment questions. And post the session, you will gain access to both the slides and the recordings, so don't worry in case you have network issues and things like that. So I will skip this. I think the main highlight is, let's keep the session interactive. When we work on problems, when we discuss concepts throughout, please chime in with your inputs on chat. Doesn't matter if you're right or you're wrong. Don't feel hesitant to ask questions. The whole point is to get your doubts clarified in a live session, right? So don't hesitate. So coming to week 3 and what was covered. So broadly, it was an introduction to CUDA programming. So we looked at various things, starting from the basic, how does a CUDA program look like? What is its structure? Then we took a quick look at the compilation flow, then at the memory allocation, data transfer from host to device, from device to host, and then the launching of the kernel that is done by the host, and then again other primitives that are used in CUDA programming, such as grids, blocks, threads. And when we write functions, we also looked at what keywords we use to declare them. Lots of things like that, right? So today we'll majorly be covering content from this week. I'll also be addressing some questions and doubts we had from previous weeks. So with that said, let's get started. So I think this was a week 1 question, and I think the answer key that was officially given was wrong. So in the live session, I didn't get a chance to discuss this, and in the last session, I think someone asked for this to be discussed. So let's do that once before we move on to week 3. So this question says, a CPI of 10 was observed from simulation experiments conducted with a perfect cache for a processor with clock rate 5 GHz, a 64 KB L1 cache having miss rate of 4% and cache miss penalty of 60 nanoseconds is proposed to be used. What would the CPI be with this 64 KB L1 cache? And you have a few options given. So I think last time we discussed it, we said the answer was 12, and then I made this correction before posting the slides. But let's actually work through that, right? How do you get to the answer of 22? So you're given that the clock rate is 5 GHz. So what is the period or the time for one clock tick, which you would get by taking the reciprocal of 5 GHz? That comes out to be 0.2 nanoseconds. And now you're told that the cache miss penalty is 60 nanoseconds. So now we are trying to convert that into cycles. I think this is not needed here. So we are trying to convert that into cycles. And why are we trying to do that, right? Why don't we work with time itself? Might be a question you're thinking of. So ultimately we are looking at CPI, right? This answer asks for CPI. So if you try calculating things in terms of time, you will have to first convert this ideal one in terms of time, and then again this one is already in time, so that's fine, but again once you get the answer you'll have to convert it back to CPI, which is what is asked, right? So the easier thing to do is to convert this one thing to CPI and use the ideal CPI that is already given to you. So now in an ideal world with a perfect cache, you know that it would take 10 cycles per instruction. But given that you are going to use this 64 KB L1 cache, which has a miss rate of 4%, which means that 0.04 times you will have a penalty of 300 cycles, which is what the 60 nanoseconds is. So this part is whenever there is a cache miss, right? 0.04 into 300, and this 10 is whenever there is a cache hit, and ideally I think it should have been 0.96 into 10, because that's when you would hit the ideal CPI, but this is still fine, right? So doing this, your answer comes out to be 22, which was what I think the corrected answer key gave. So hopefully this is clear. Any doubts on this? I'll just pause here for 30 seconds. So, sorry, how is the 2 nanoseconds, 0.2 nanoseconds coming from? I am assuming that's just 1 by 5 gigahertz, right? So, gigahertz is 10 power 9, which you take a reciprocal, it becomes nanoseconds, right? 10 power minus 9. And similarly, you take a reciprocal of 5, 1 by 5, that becomes 0.2. So, if you say the frequency is 5 gigahertz or the clock rate is 5 gigahertz, the time or the period of one clock tick will be 0.2 nanoseconds. So that's just the period being the reciprocal of the clock frequency. Is that clear? Great. Anyone else? So I give you that pause of 30 seconds so that you can look through the solution a little more carefully and ask me. It doesn't matter, even if you don't understand a small part, feel free to ask. Otherwise I can just move on from one question to the other. The point of giving you some time in between is to go through what I just explained and see if it's clear to you. Okay, let's move on. Right, so these are a couple of topics I said I would explain after week 2, right? I think I said I would explain the whole SIMT versus SIMD and the GPU memory type. So those are the two topics I've picked up for today. So I think we went through SIMD in detail, right? So we said that, so for people who don't remember, SIMD stands for single instruction multiple data, where you have one instruction and it's a form of using data parallelism, right? Where you have one instruction that, and the instruction works on different parts of data. And I think we looked at some examples of vector processors and things like that, which use this SIMD notion. And after that we looked at a GPU execution model, and we said that that is SIMT, where it is very similar to SIMD, but what it actually uses is threads instead of SIMD, which uses just these multiple data lanes, right? So the main difference that you have to remember between SIMD and SIMT is that in SIMT there are different threads that are running in parallel, and that's how actually you can think of SIMT as something that uses SIMD underneath, right? But the only difference is it uses this notion of multiple threads, and that's what you see in your GPU architecture, right? Now that we've studied week 3 of CUDA programming, I think you'll find it easier to appreciate this concept. For instance, we looked at a small addition program where we said that every thread would handle the addition of one element, right? And there would be multiple threads handling different elements, and that's how we get parallelism. So that is the idea behind SIMT. But I said, and this slide, kind of the slide that is included in your curriculum, touches upon the basic differences, right? But there is a lot more to that. So I'll touch upon two aspects maybe very briefly. So one is the ease of programming, right? If you look at SIMD, you actually have to do this vectorization or breaking down data into multiple parts and writing code by yourself, as in it's not automatically done. But with SIMT, we looked at sample programs this week, and we saw that all you had to do is write CI equal to AI plus BI, and you would also say that a particular thread handles this element, right? One line for that. So in terms of programming, you can think of SIMT as a much easier way to use SIMD. Underneath, this data parallelism is still happening, right? One thread is dealing with one data element in the example we spoke about. So that data parallelism that SIMD uses is still happening, but you don't have to manually write it that way, right? So in terms of ease of programming, SIMT is much better than SIMD. And the other main difference, which I think you will understand and appreciate better after a few more lectures, is that SIMT also, since it deals with the granularity of threads, it can control this execution and branching behavior of threads much better than SIMD. So for instance, if you wanted to do something different, so this is called divergence, right? So something simple like you want to test a particular condition, and if that's true you want to do something, and if it's not you want to do something else. SIMT kind of enables you to do this much better and much more easier, right? Those are two aspects in which SIMT and SIMD are different, right? So in terms of GPUs, it's always SIMT, but how SIMT and SIMD are different is very minor differences, right? Under the hood, it's still going to be here it's going to be multiple threads working on different pieces of data. There it's not threads, but it's still the same idea. Your data is partitioned into multiple parts, and the same instruction is executed, and the instruction may operate on these different parts. So they are very similar. So this difference might be a bit hard for you to understand very clearly, but you can think of it in two ways. The two ways that I explained to you, one is the programming ease, second is the handling of divergence. Both of those are, I think, key differences of SIMT from SIMD. Okay, so this is about this concept. So is this clear, or would you like a more detailed explanation? If so, I can do that next week, but I think it goes a lot deeper into the architectural aspects and may not be necessary from the purpose of this course. If you're interested, of course, if multiple people say that this is something they would like to understand better, I'm happy to spend more time on that. Anyone? Is this clear enough? Okay, I will assume that it is okay. You're interested to know more. Okay, I will see if I can cover that somewhere in the next class, or maybe whenever I find little time, right? So some weeks are heavy on numericals and problem solving, where 2 hours just goes by very quickly. But there are other weeks where questions are mostly theoretical and you don't need as much time to solve them. So I will, depending on how the weeks are structured, I will try to touch upon this difference a little more in detail and in depth, because I think some of you are interested in learning more, and that's always good. And today after the session, I'll also add a couple of links outside your course notes where you can go look up these concepts, right? Maybe that will also be helpful in the meantime. So I'll do that. Great. Uh, Moving on. So the other thing I said is I would cover GPU memory types, because I think there was a question on cache memory and constant memory, and people were not very clear on what are the types of memory, right? So from the perspective of your course, sorry, the term thread that we are using here is similar to threads created by pthread in a C program. Okay. The idea is the same, but typically when you talk of threads, you might be uh, using them in the context of CPU threads. Here the only difference is we are talking about threads that are running on the GPU, but the idea of threads itself, I think it is the same. You can take it to be the same, but okay. But if you think about how this is done, right? For instance, one more difference that I can think of is if you use a library such as pthreads, like you're saying, the programmer has control on how these threads are created and joined, right? That's one level of parallelism that you do. Here, the thread idea is kind of both programmer defined and implicit. So for instance, you define this whole grid dimension and blocks per threads and things like that, but ultimately there is also the scheduler that comes into place that decides how many of these threads to schedule at one go, whether the memory is sufficient for them and things like that. So those are some differences, but the idea of using multiple threads, I think, is similar across CPU and GPU. Okay, if that is it, moving forward. So I think these three types of memory we already looked at in your course lecture, right? The local memory, shared memory, and global memory. We'll go a little into details of how these look, right? So this is picked up, I think, from CUDA documentation, and they give you a more detailed kind of view, right? So you can, the different types of memory here are indicated in terms of whether it's read only, whether it's read write, and whether it's per thread, whether it's per block, per grid, right? So you can see that global memory, constant memory, and texture memory. Okay, there's another question. Let me read that. Suppose we had two operations, one add and one subtract, in the same kernel function. Will one thread work on both operations, assuming thread ID computed is the same for both the operations? Okay, I see your question. I think that would be the case, but I'm not sure if there are any exceptions or corner cases in which there would be multiple threads doing it. For instance, if you don't have a dependency, right? So in this case, you're saying you have one add and one subtract. And I'm assuming both of these use the same inputs, but they're not dependent on each other. So there might be CUDA primitives using which you can make it such that these happen concurrently, and it could be that uh, they are handled by different threads, but by default I think they would be handled by the same thread as far as what is covered so far in your course is concerned, right? I think they would be handled by the same thread. But there are things like CUDA streams that I'm thinking about right now and that I'm not very sure of, but there are ways in which you as a programmer can make sure that but I think CUDA streams would still apply to multiple kernels, not two different things in the same kernel. So I think it would be the same thread, but let me get back to you on this. I will just note down your question in the meantime. That's a good question. Yeah, I will get back to you on this. For the moment, I feel it is one thread, but let's see. It would be interesting to see if there are exceptions to that and if there can be different ways of doing that. Okay, moving forward. Where were we? So we were talking about the three different types of memory, all of which you can see here are indicated as host, which means that it is in the CPU DRAM, right? And there are other kinds of memory, which I think some of which we already looked at, right? Local, shared, and global. And apart from these, there are registers that was also discussed in the course. But this slide, I think, gives you a nice visualization as to whether it's per block, per grid, per thread, and things like that, right? So I will leave it here for your reference. I think most of it is just repetitive from your course content. The other thing that I wanted to also put in here again is, for instance, are some of these memories cached? And again, like we saw in the previous slide, who can access this, right? Is it all threads in a block? Can the host also access it? You can see that for global, constant, and texture, it is set as off chip first of all, and it is said that all threads can access it, also the host can access it, right? So these things are again useful. They are slightly more nuanced, so I don't think it was covered in your original lecture material, but if you're interested you can go through this. Also, which of these types of memories are cached, right? You can see that some have yes and some have no, so that's about the whether it's cached or not. And again, what is stored in each of these types of memory. For instance, I think the question was on constant memory. So it says constant memory is useful for uniformly accessed read-only data. And similarly, you have why texture memory is used, why local memory is used, and all of that. So go through this a little bit if you're interested, and that will help you appreciate the types of memory more in detail. And the other question that was there as part of this memory spaces was, I think, cache memory, right? So, and here is where I think the question was asked. So I think what we discussed in class was based on the Fermi architecture. So I've just put a couple of other architectures here as well, just for you to remember that a lot of features that we discuss, if we discuss Fermi, right, and today Ampere might be one of the newer architectures out there, a lot of features have changed drastically. For instance, you will see that there is something called an RT core here, these tensor cores and all that, right? Which is not at all there in Fermi, not at, probably first generation in Tesla, I'm not sure. But a lot changes from generation to generation. So keep in mind, when you answer questions, when you think of features, when you learn of something in class, that a lot of things change because you're learning about hardware features. So as the hardware evolves, a lot of these features and the architecture of the GPU itself changes. So a good way to look up the architecture of GPU, whatever you want to, for instance, if you wanted to look at the Ampere architecture in brief, you can go look at GPU white paper, right? So NVIDIA, if you're looking at NVIDIA architectures, all of these are NVIDIA architectures, NVIDIA would publish something called the architecture white paper. It would have a lot of details that may not be what you're looking for, but it will definitely have this diagram of the entire GPU architecture as well as a zoom in of 1 SM, right? So that's something you can look at to see how the architecture has changed all the way from something you learn in class, which is I think Fermi or Kepler, to the latest GPUs that are out there, right? Keep that in mind. And I think the question asked was about cache memory. So you can see here that there is an L1 cache. I don't know if it's very clear to you, but there is an L1 cache. And the question asked was, is that per SM? And it is per SM, right? Unlike constant memory, which I think is global, it's shared across all threads. And so that was the answer on that. So I think that is about it for the week 2 recap. Any other questions or any general things that you want to know? Maybe they were not covered in class. Maybe you're just curious about something. Is there something like that? Feel free to ask. I will note down the question in case I'm not sure of the answer, and I'll get back to you in the next week. Can you please show or explain how to run CUDA programs in Visual Studio? Okay, I can check with, I think there have been tutorial videos posted that help you do this, but I haven't gone through those in a lot of detail. And I can check with the regular TAs who are kind of responsible for that as to whether they can possibly come and give you a 10 or 15-minute overview on how to run programs. Is anyone else facing issues with that? It need not be this particular thing. Do you have problems in doing the hands-on assignment? Okay, in tutorials they only showed in Linux platform or Google Colab. Okay, I'm assuming that's the recommended setup that you are asked to try on. So why is that not working for you? Okay, there's another question in the meantime. Integrated GPU takes CPU RAM. It is reserved in RAM. Okay, that's again an interesting question. So yeah, integrated GPUs do use the CPU RAM itself, but as far as I know, there is no reservation of memory. So for instance, if you say there is 8 GB of memory, there is no hard and fast partition saying that 6 GB is used, 6 GB is for the GPU and 2 GB is for the CPU. There is nothing like that. It is kind of completely shared, right? So Yeah, this I think I'm fairly sure about. So it does use the CPU RAM itself, but there is no reservation as such. But you can do some things like pin a memory page, right? So there is something called pinned memory, where so on the CPU side, because we have memory management options such as paging, right? Demand paging, where you bring in a page to memory, you swap it out and things like that. It can so happen that your memory might not, whatever you're looking for might not be in memory because it is swapped out, and that can sometimes be a problem with shared memory, where the GPU also shares the same RAM, right? So I think pinned memory and things like that are useful in. So if you enable pinned memory, it basically is a directive saying, please do not swap out this page. I want this page to always be in memory. So I don't know if that's something that's covered as part of your course, but again, I'll check that, and in case it's not, I'll briefly talk about how the RAM is managed between the CPU and the GPU in an integrated setting. That's also a good thing to know. But as far as I know, there is no reservation as such. Hope that answers your question. Okay, to the other question. So if a particular configuration was shown in the tutorial, right? Please try and follow the same configuration, because I don't think the TAs would be able to address individual issues that you're facing because you're trying out something different. If it's merely an OS thing, you can probably use a VM. But if it's collab, I think whatever they showed should be fine, right? I am not very clear on what was shown because, like I said, I didn't follow the tutorial videos very closely. So if you have a particular, okay, we need NVIDIA GPU to use Visual Studio. I see. Okay, so this might be something I can ask the TS, but I am guessing that they will ask you to follow the collab tutorial that was demonstrated. So if you are trying out something new, they might not be able to support those different configurations and issues you might face with that. If you have a particular issue, you can ask me and I'll probably try and resolve it. But it is outside my kind of what I have been asked to do through these live sessions, to actually demonstrate how to get your programs running using a particular configuration. So I will not be able to do that. If you have a particular error or something like that, please post it on the discussion forum also. You need not wait till the next Monday to ask me. And if you want something different from what was demonstrated, you can also explain your reasons for why you want that, and you can see if the TAs are willing to either point you to some resource, or I see it's an OS issue. Okay, you can do one thing, post it on the discussion forum right away, like after this session. I hope you're aware of how to get to the discussion forum. So on the course page, there is a button saying ask a question. Using that, you can post your question, right? And the official TS who are handling these things will respond to you, and that should help you out. They might not be able to give you a video showing how to do this, but I'm hoping they'll at least point you to a resource. And please explain why you're unable to use the Linux or Google Colab that was demonstrated, right? Like you have said here that we are using Windows except in institutions. So feel free to say that, and say that you're specifically looking for instructions regarding this, and they should be able to help you out. Is anyone else facing issues? Sure, no problem. Anyone else facing issues on getting a sample CUDA program running or something like that, or mostly were the tutorials enough and good to reproduce? Okay, let's move on in the interest of time. And general instruction again, if you have issues with anything, please post on the discussion forum, especially for your programming assignments, right? Here in these live sessions, the idea is to mainly discuss your MCQ kind of questions, not really the programming assignments or getting things running and debugging errors. So use the discussion forum to bring up all those issues, and the TAs should be able to help you. I think there was a particular question also posted that they have responded to, that I've also put in these slides. So we'll take a look at that as we move through. But since we are kind of running short of time, I'll move ahead. So again, I've kept the recap very short. We will see today's problem solving session, and based on that, if you're not clear on some concepts, I will again go into them in detail in the next session. But this is just a brief recap, right? So these, you would have already been familiar with these terms of host and device, right? Host is typically used in the context of a CPU, and device is used in the context of a GPU. And you can think of any C program as a valid CUDA host code, and if you have device code additionally, it cannot be compiled by standard C compilers. So that needs a particular compiler. Assuming this is on NVIDIA GPUs, you will have to use the NVIDIA C compiler, which is NVCC. And yeah, this is the memory layout. So this is again assuming a discrete GPU, right, where you have this notion of a host memory and device memory. In case of an integrated GPU, it would be a single RAM, as someone just pointed out, right? The RAM is shared between the CPU and the GPU. Okay, in the output after running the program, there is no blank line at the end, and in the output file provided, there is a blank line at the end. Will this make my output not valid? I think that is a minor difference, but again, I have not seen this programming assignment and I have no idea if the instructions provided are very specific, right? So I know that some people use automated assignment evaluations and things like that, where even small things can cause it to break. So again, feel free to ask this on the discussion forum, right? Any doubts on the programming assignment, the input format, the output format, please ask on the discussion forum, so that the actual TAs who are evaluating those will see your questions. I don't do that, so I don't want to give you a wrong answer that will potentially cause problems, right? So ask it there. It's good to get official clarification on that. Great. Right. So yeah, so I was talking about host and device memory. In an integrated setting, you would not have these as two distinct sets of memory, right? It would be the same CPU RAM, that as we spoke about in the previous sessions as well. So what else? I think these are all fine. So I think I just had one question that I saw for, so if whoever asked this question is here on the call, you can note down the corrections. I think there was just an issue with the URL, right? So they've kind of fixed that and given you a different command for whoever faced this issue while trying to install stuff. So this will be there in the slides. Feel free to use the right command. So with this, we will get started with today's problem solving. In the meantime, are there any other questions or any other topics from week 3 that you did not understand that you would like me to go into detail? Is there any such topic? Think about it. I'll give you another 30 seconds and then we'll move on to the problem solving. Okay, you have a query regarding programming assignment for week 4. I haven't taken a look at that, but yeah, feel free to ask the question first, and then I will see if that's something I can answer next week. I don't know when is the deadline for this, so I don't know if me answering it next Monday will help you. But ask your question anyway, then we can see. Anything else? Okay, you're able to compile and run it using the NVCC command on your Windows PC. Do you need to use Collab? Okay, this is again an execution environment thing. I would say it's fine if you're able to run it, but I don't know if there are explicit instructions that ask you to use Collab or something that they're looking for. So get it double checked from the official TAs, right? So ask on the discussion forum again. Great. So typical rule of thumb for you guys is if it's a question on how do I run something, or I'm getting an error in running this, or maybe something like this, the input given is like this and my in output format given is like this and my output is like that. For all those sort of things, it's good to check with the official TAs because they'll be the ones evaluating it. But if you have conceptual questions, for instance, I tried out this particular implementation this way and I'm not able to understand what's happening, then I can probably spend some time on that. But again, that will be only after you submit your assignment, right? Because we won't be able to discuss an assignment question while the deadline is still ongoing, because you're supposed to do that on your own. So with anything pertaining to execution environment or installation errors or input output formats, ask on the discussion forum. After an assignment deadline has passed, if you have doubts on the conceptual part of it, on how to implement it, or I implemented it a certain way but the solution given was something else, then feel free to bring that here and we can take a detailed look at it. But by default, I don't look at the programming assignments or the conventions and the environments that you're asked to follow. So I might not be able to answer your questions well enough, and I don't want to give you wrong information because your evaluation might follow different policies. So that's kind of the long answer to that. Okay, so we went through all of this. Let's do a couple of problems and then take a break near the 1 hour mark. So let's keep it interactive. I will give you enough time for all questions, right? So look through the questions, think about the answer, and post whatever you think is the answer on chat. So the first question, which of the following statements is true? A function declared with the keyword device is executed on the host. A function declared with the keyword global is callable from the device. A function declared with the keyword host is executed on the host. A function declared with the keyword device is callable from the host. Take a minute, read it again. Okay, we have one answer, C. Okay, C. function declared with the keyword host is executed on the host. Anyone else? Anyone else? Someone thinks the answer is not C? Okay, let's take a look at the answer then. It is C, a function declared with the keyword host is executed on the host. And you're asked for which of the statements is true, right? So why are all of these not true? So functions with the device keyword are callable only from the device. So option D says from the host, which is false. And a function declared with device can only be executed on the device. So again, A is false. Then finally, functions declared with global can be called only from the host, which is again option B is incorrect, right? So you're left with C, and C is true. And just as a recap, this is kind of the table that was discussed in class, and this is what the question is based on, right? So go through this again. It's kind of a direct recap question. So for instance, if you have device, it can be executed on the device, callable from the device. If you have global, it's executed on the device but callable from only callable from the host, and so on, right? So go through this and that should help you answer this question. Any doubts on this? Okay, if not, let's move on. Question 2. Suppose you want to allocate memory of size total SZ bytes on the GPU device for a float buffer D underscore A. Which of the following options represents the correct function call for achieving the same? So you have 4 options. I'll give you a minute. Look through them and tell me which you think is the right one. Okay, A. Anyone else? Is something confusing you in the question, or is the question clear? To the people who are not answering, right? I'm just trying to understand what is difficult here, so that I spend more time explaining that. That's kind of the point. Okay, we have one more answer, A. Fine. Anyone else? If you don't understand something in the question, feel free to say that I'm unable to understand this part of the question, or maybe you just don't remember what is the syntax of CUDA malloc, right? That's also fine. But if you're not understanding something in the question or in the options, please feel free to say that. Okay, I think we've had enough time. So let's look at the answer. It is A, and I've one additional thing I wanted to tell you guys is I think your lecture notes anyway have the syntax of all of these functions. But another good source to go look at it is the official NVIDIA CUDA documentation, right? Because as the CUDA versions change and as new versions get released, some of these syntaxes might actually change. So given that you are also going to be programming using CUDA and using all of these functions, it's good to go refer to the official documentation. So I've put in a screenshot from there here. So you can see that CUDA malloc takes a void star star pointer to the device memory and also the allocation size in bytes, and it also says what the function does, right? It says it allocates memory on the device, and you can also see that there is a CUDA error underscore t. So if you look at the function documentation in detail, you'll also get information on what is the return type and things like that. So feel free to go look that up. I put in a link here to the NVIDIA documentation for CUDA malloc. So there is a question slash comment. D underscore A holds an address of a pointer variable. So we tell the compiler using typecasting. Okay, sure. Right, so about this option. So here your D underscore A is a float buffer. Yeah, sure. That can be taken as that. So look, broadly the syntax is the pointer and the size in bytes, both of which are given here. So it's as simple as following that convention, right? So yeah, that's the answer for this. I think it's fairly straightforward. Any doubts on this? Okay, I think we are close to 8 o'clock, so we can take a 5-minute break now. So my clock shows 7:57, so we'll come back at 8:02, right? Use the break to just context switch and come back so that you can listen for another hour without feeling too saturated. So I'll see you guys again at 8:02. I'll stay on the call, but we'll resume at 8:02. Okay, let's continue from where we stopped. So here's the next question. Suppose you want to copy the elements of a floating point array h underscore a from the CPU or the host to a floating point buffer d underscore a on the GPU device. The number of elements of the array is 1024. For a system where the size of a float is 4 bytes, which of the following options represents the correct CUDA memcopy call? Take some time, read through the question again if you want. I'll wait a minute for your answer. Okay, B, B, anyone else? No other answers? Does everyone agree with B? Okay, let's take a look. It is B. So first of all, coming to the size, you're told that the number of elements of the array is 1024 and each, it's a float array, right? And the size of the float is given as 4 bytes. So the size in bytes will automatically become 4096. So with that, you just need to figure out, you know the call is memcopy because you're copying data. You need to figure out if it's d underscore h, or with this set of options I think you don't even need to do that. Once you get 4096, you know which option it is. But ideally you need to know the source and destination format, right? So that's why I put this. Not sure if it's visible. Let's temporarily enlarge it. So this is again from the NVIDIA official documentation. So you can see that CUDA memcopy tells you specifically that it should be destination followed by the source and followed by the size, and finally the direction, right, which is missing here. So I think in the course material that the few examples that we looked at, we specifically also had something like host to device copy or device to host copy or something like that. But that's where I wanted to also tell you that some of these values can take a default value, right? For instance, this kind, which is the last argument that CUDA memcopy takes, tells the type of transfer, and you've seen examples where that is specified manually, saying host to device or device to host. But if you actually look at the documentation, it says here that the default is 4, which means that if you don't specify it, it can infer the direction of the transfer from the pointer values, and it also gives you the disclaimer that this requires something. So for as far as this question is concerned, with the options that you are given, you know that it has to be B, right? There is no confusion about this. But this is just extra information, and this is why I tell you to look at the official documentation, right? You realize interesting things like this, that it is possible for something like the direction of copy to be inferred using the pointer values. So yeah, I think that was about it. So the other thing I was saying, so size in bytes I think we went through, kind we went through. So destination first and then the source. So you want to copy it to d underscore a, which is the destination, that comes first, and your source is h underscore a, so that comes next. So that's everything that's there for memcopy. Any doubts on this? Another tangential question that maybe I would ask you is, when would you use something like host to host? Any ideas? This is again unrelated to the question, but just for curiosity, right? You see that kind has 4 types, and 4 or 5 types actually, and it's host to device, device to host. So you see host to host here. Why might that be necessary? I'm not going to answer this, but think about it. Okay, if there are no other questions on this, let's look at the next one. We don't use it because we have another option in C to do this. Okay, C as in the language. Okay, so why do you think CUDA provides that option then? If it was not needed in any use case, right? It's a waste for them to actually design that functionality and then provide it to a user. So there has to be a valid use case somewhere for them to provide this option. You're right in that we might not be using it very frequently, but why does it make sense to even have this as an option is what I was asking. But yeah, think about it. It's not very relevant to this question as such, but think about it. So let's move on to the next question. Consider the following pointwise multiplication kernel snippet. So this is a multiply, and this is your C of I equal to 0 and C of I plus equal to AI star Bj, Bi. This is your compute operation here, and so this is just pointwise multiplication, right? You take the one element of A, multiply it with one element of B, and you add it. So C is initialized to 0, and thereafter you just keep adding this, and this is what we do. Now with this code in mind, suppose a total of 1024 threads are being launched for the kernel. The number of elements for each buffer A, B and C are also 1024. What is the total number of floating point operations involved in the compute operation? So the compute operation was this. There's a comment that indicates so. What is the total number of floating point operations involved in the compute operation? That is the total number of floating point additions and floating point multiplications. So you will have to count both the additions and the multiplications, and what is the total number of such operations involved to do this particular compute operation. That's your question, and you're given the number of threads, and you're also given the number of elements for each of these A, B and C. Take a minute for this again, because it might take you some time, and in case you want me to go to the previous slide, I can do that as well. Let me know, just let me know on chat, and I can move over to the previous slide. Okay, sure. I'll move over to the options in case anyone wants them. Yeah. Okay, 2048, which is option C. Great. Anyone else? So think of, if you want to break this down, or if this looks too difficult to solve, think of how many operations every thread does. And then all you need to do is multiply that many number of operations by the number of threads. Okay, C 2048. Great. Anyone else? I'll wait another 15-20 seconds in case someone else is solving it. Okay, if not, let's look at the answer. It is C2048. How do we get that, right? Like I said, first let's look at the number of operations each thread will have to do, right? Which is basically this compute operation. So you have one multiplication here and then one addition here. So that gives you two operations. And you're told that there are 1024 threads being launched. You're also told that there are 1024 elements in each of these buffers. So you can assume that, unless you're explicitly told otherwise, you can assume that each thread will be handling one of these elements, like you see here, right? This calculation is basically used to divide that. So if you have an array of 1024 elements, depending on you can map a certain number of elements to a thread, right? That can be one, that may not be one. But in this case, since you are explicitly told that there are 1024 elements and 1024 threads being launched, you can assume that every thread handles one element of the buffer. So in that case, you have 1024 threads running, and each of those threads does this one add and one multiply, which is two floating point operations, and that 1024 into 2 gives you 2048. That's how you get option C as the answer. Is this clear? Great. So another side note on this floating point operations, I think we spoke about it in one context, as to this is a metric that is used to measure the compute capability of a particular GPU or any hardware for that matter, right? But the other way you can use floating point operations, and that's actually used also, is to measure the computation involved in a particular implementation of an algorithm, right? So for instance, this pointwise multiplication, in this particular method where I used one multiplication and one addition, you can actually come up with a theoretical complexity for this, right? And similarly, you can also come up with the flops as a metric. And if you have some other method to do the same thing which is maybe inefficient, it might result in more computation. So this floating point operations is also used in that context. For instance, today there is a lot of AI and ML workloads, right? So with all these deep neural networks or DNNs, you might see people talking about the flops it takes for a forward pass. That's basically how many operations does it take for a forward pass through that network. And again, it is a very implementation specific detail. Like I was just talking about the pointwise multiplication here. One of the most common operations used in deep neural networks is convolution. So depending on how you implement convolution, the number of floating point operations it takes for convolution might change, right? Depending on the actual algorithm or the actual implementation you choose for convolution, it might change. But regardless of that, the floating point operations is a metric by which you can compare different implementations of the same thing. So if you have two implementations of convolution, you might see how many floating point operations method A takes and how many method B takes, right? That's another side note on floating point operations or flops. Okay, moving on. So again, there are a bunch of these questions that are long, so I can't put them in one slide without kind of really going small on the font size, and that's a problem. So I will scroll between slides, so feel free to ask me to do that. So here is the next question. Let us consider a kernel which takes as input two one-dimensional input buffers d underscore a, d underscore b, and produces one-dimensional output buffer d underscore c. The associated host arrays for each buffer are h underscore a, h underscore b, h underscore c respectively. Let us assume that the size of each such buffer is sz. Consider the following host code snippet for the same. So there is some code for initializing the host arrays, that's kind of not gone into detail here. Then there is code for copying input buffers, which involves two CUDA memcopy calls where the size is populated and the direction. Remember this direction that we were talking about a few slides back, right? Host to device. So here, for instance, both are host to device, but the other two fields are left blank here. Then there is some code to launch kernels, and finally there is some code for copying the output buffers, which is again a memcopy call, but the direction is now device to host and the size remains the same since all three have the same size. Now your question asks, each of the three lines of code has two blanks. So pick the correct option from the following. So basically the rest of the code is abstracted to you. You don't care about this initialization. You don't care about this kernel launching code. You only care about these three lines of code, which is copying the input buffers, copying the output buffers. And you're asked about these blanks. Now what you have to do is match these blanks. So here are your lines 1, 2 and 3. They are numbered in case you didn't notice, and the two values for each of those lines are given in your options. So again, this might need a bit of scrolling between the two slides, like I said. So if you want me to hover at the previous slide, what you can do is to, okay, we already have an answer D, great. For someone else, if you want me to scroll back, please let me know and I'll do that. Okay, destination comma source, so answer is D. Okay, anyone else? Okay, let's look at the answer if no one else has something to say. So it is D, and like someone pointed out, it's a straightforward thing once you realize the, yeah, first copy the two arrays to the GPU, then copy D underscore C back to H underscore C. Right, that's exactly it, right? It's a straightforward thing. You need to know that it's destination comma source. So first you're copying from host to device. So both of these will be D first and then H. Whereas in the output, you're doing the reverse, right? So you'll have H first and then D. Any doubts on this? No doubts. Okay, anyone else? If not, let's move to the next question. Yeah, so recall the vector addition kernel taught in the lecture. Consider the following CUDA thread launch call. Vector add 256, 1024 with arguments DA, DB, DC and DN. Which of the following is correct? 1024 thread blocks containing 256 threads per block are launched. 256 thread blocks containing 1024 per block. Total of 1024, total of 256. So we have one answer that says B, we have one more that says B. Anyone else? I'll wait a few more seconds in case someone is still reading through the options. Okay, if not, it is B, and I think there is no explanation needed for it. So the convention is just thread blocks comma threads per block, right? So you have 256 blocks and each of those will have 1024 threads per block. That's about it. So I think uh, I'm assuming there are no doubts, but in case I'm wrong, please post your question on chat. So in the interest of time, I'll just move to the next question. Consider the following kernel function calls and the following statements. So again, you have K1, K2, K3 with different threads and threads per block, and you have six statements about these three kernels, and what you're supposed to do is pair these function calls, which are numbered 1 2 3, to the right statement out of the six that are given here. So since it's a lot, I'll let you guys read it for yourself and take your time to figure out the answer, because it involves a lot of, I think, parsing through the options. So I'll give you 2 minutes for this. It's very similar to the previous question. You just have a lot more kernels and a lot more statements. Okay, we have one answer that says C. Okay, one more person thinks it's C. Anyone else? Any other answers? Okay, if not, let's look at the answer. So it is C. I think whoever answered got it right. So let's once look at the options, right? So 1 matches with F. So 128 in 2024 would give you this 131072. You can cross check that, but that comes out to be right. So that goes with F. Then 2 goes to A. So 16 thread blocks containing 1024 threads. Again, that makes sense looking at the numbers. And then 3 goes with B, which is 4 into 1024, which is a total of 4096. So that's how you get these. You can also go through the other options and see why they don't fit the bill, but I'll skip through that, and since it's kind of straightforward, right? So for instance, I think in one of these it is reversed, the number of thread blocks and the number of threads, and in something else the total number of threads is wrong. Yeah, you can figure that out. I think it's straightforward. Any doubts in this question? If not, let's move to the next question. Consider the following incomplete kernel code snippet. So you have something, a vector subroutine, which basically does a of I minus b of I if I less than n. But the I statement, which is, if you remember from your other sample programs, it is the assignment of these individual elements to threads, right? That is left blank, which you have to choose from these options. So broadly, the function takes two input arrays A and B and computes an element wise subtraction and populates that into C. What should the appropriate value of I be? So you have four options here. So think through this. How would you assign these elements to threads? Okay, we have one answer that says A. Anyone else? Any other answers? Does someone think it's not A? Others who agree with A? Right, okay, let's look at the answer. It is A. So let's talk a little bit about how it is A, right? So assuming that you have this, I hope this is sort of visible. Okay, we have a question on this. If we remove the if condition here, then what will happen? Okay, if I less than n, okay, here the size of both those is n. So I'm assuming you'll hit some kind of error because there are only n elements, right? So you want to do that programmatically to ensure that your accesses don't go beyond n. But if you actually run this, what will happen is something I'm not very sure of. You can just try that out. Just write a simple program like that, like this, that does sum or subtraction or one of those, and see what is the actual error that you get. Is it a compile time error? Is it a runtime error? That will give you good insights on how NVCC works, right? That's a good question. Look that up, and if you don't find it, I can also try and look into that. But why is that there? It's just there for the size check, right? You have an element, so you don't want to go beyond that. Okay, so coming back to this mapping of elements to threads, right? So because we have this two-dimensional hierarchy where we talk about blocks and then the threads per block. So if it was directly just one dimension where you have, let's say like in the previous example, where you have 1024 threads, how would I assign each of these elements to the threads? I would just need the thread ID, right? I could just assign it based on that. But now you have this hierarchy where you have a block number and a thread number within that. So how do I then address a particular thread? First, I try to find out which block it is in, which is done by the block ID, and then you multiply that with the block dimension of x, which basically tells you the blocks, which is dependent on the block size. So let's say here I think the block size is 256, right? So let's say I'm trying to get the ID of thread 3 in block 1. What do I need to do? I take its block ID and I also multiply it. I also take the block dimension into account. So that would be 256 here. So that would give me this offset right here. Maybe I'll just draw this out with a pen. So let's say I want to get this particular thread, right? How do I address it in this hierarchical scheme? First of all, I figure out what is the value till here, which I get by doing this multiplication, block dimension into block ID, right? After that, it is just given by the thread ID. So this numbering that you see here is just the internal thread ID, which is 3. But because we have this hierarchy, we also have to account for the previous blocks, right, in our assignment. So that's how you get this latter part of the equation, and then you just use the thread ID of x. So this hopefully clears up why this assignment statement looks like this. So again, I think I gave this example before also, right? If I asked you if you had something like a book where you are trying to refer to a particular word, right, in this particular page itself, how would you refer to it? Now if I just had a number for every word, then I would say word number 25, right? But as human beings, what we tend to do naturally is to say the third word on the second line, right? This is very similar to that. You have a hierarchy of block and then within that thread. So if I told you the third word on the second line and you had to translate that to the word number, what would you do? If assuming that every line had a certain number of words, you would first try to get this line, this boundary, right? Till here, how many words have been consumed? Then after this, you would just take the word number in that particular line, which is 3, right? So if this line had 20 words, you would just take 20 plus 3. If this was on the third line, then both the lines before it would have 20 each. So 20 into 2, and then plus 3. So that's kind of the basic intuition for how you get this. Is this clear? Any doubts on this? This concept will keep on being used throughout, and you'll see more complicated versions of it, right? Like a two-dimensional thing and all that. So it's good you understand at least this part very clearly. You'll see it with x and y also. So at least if this is clear, then you can look at things like that. Any doubts on this? Okay, if not, let's move to the next question. Okay, again this is a copy kind of question. Suppose you want to copy a device buffer D underscore C from GPU to host array H underscore C. Size of the buffer is stored in size underscore bytes. Which of the following represents the correct call to CUDA mem copy? Any answers? Okay, B. Anyone else? Anyone else? Okay, let's take a look at the answer. It is B. Again, I think it's straightforward. You're given the size, the direction of copy is device to host, and your destination is H, and your source is D, which makes it option B. Yeah, the ones that say host to device are wrong, so D is wrong. So with device to host, you have 3 of them. But again, looking at the source and destination convention, I think it's clear that it's B. Any doubts on this? If not, we'll just move to the next one. Okay, I'm assuming there are no doubts. Let's look at the next question. Consider the following kernel specific system variables and the subsequent statements. So these are your 4 variables, and here are some statements made. So this is again match this with this. So your options match these 1, 2, 3, 4 to A, B, C, D. So again, read through them, take some time to do the matching. I'll give you 2 minutes for this. Okay, we have an answer that says B. Anyone else? Okay, we have one more answer that says A. I'll wait a little longer in case someone else is solving the question. Okay, so I think it's A2. Okay, no worries. Anyone else? Okay, let's look at the answer. It is A, so let's look at what that is, right? So grid dimension dot x maps to number of blocks in dimension x of a multi-dimensional grid. Block dimension dot y maps to number of threads per block in the dimension y of a multi-dimensional block. Block idx dot y maps to block number for a thread in dimension y, and thread idx dot x maps to thread number inside a block, right? So remember that hierarchy again: grid and then blocks and then threads per block, right? So I don't know if this was a little confusing. I don't think I have an explanation. Okay, I have some explanation. So yeah, let's go through this recap a little more to understand how you get this. So when we use a kernel call, here in this case vector add is the CUDA kernel, and the threads are launched in a two-level hierarchy. So we specify a grid of threads to be launched, and this grid is arranged in a hierarchical manner: number of blocks, number of threads per block. And you also have this notion of an x and y dimension, right? And that's where this whole grid dimension dot x, so you can have a multi-dimensional grid, right? Instead of, I think in the example we saw previously, we just saw one dimension, right? But you can have a multi-dimensional grid. I think that was discussed in one of the examples in the lecture, but maybe I'll even put in a more pictorial example next class so that you can see how exactly the mapping of elements to threads happens. But remember that there can be multi-dimensional grids. So then you have things like the x dimension, and similarly for the block also you can have an x and y dimension. So it's just extending that same concept that we saw into multi-dimensional world, basically into a 2D world where you have an x and y dimension. That's about it, and this is the conventions that are this is the explanations of the terms that was, I think, given in the lecture, right? So the grid dimension is number of blocks in the grid, whereas if we look at grid dimension dot x, it is the number of blocks in the x dimension when the grid is multidimensional. Block dimension normally means number of threads per block, but block dimension dot x for a multidimensional block refers to the number of threads per block in the x dimension. And if it's a single dimension, as you can think of, block dimension would be equal to block dimension dot x. And similarly, you have block idx dot x and thread idx dot x, which is block number for a thread and thread number inside a block, which I think we went through in the previous example. So this should be clear. So it's just a two-dimensional arrangement instead of a one-dimensional that we saw earlier. So hope this one is clear. I'll just pause for 10 seconds to see if you have any questions. And if this is not very clear, feel free to post that also on chat. We can spend some more time talking about this two-dimensional grid and two-dimensional block in the next session. Okay, if not, let's look at the next question. I think we have one or two more to go. So here's the next question. Consider the following kernel snippet. So you have an assignment of threads to elements as usual, and ci equal to 0 if I less than n, ci equal to 0, and you have a for loop that runs from 0 to less than m, and this is your compute operation, which is again doing a pointwise multiplication and adding it, right? So you're doing a multiply and then adding it to the same C of I. Now for this kernel, so this is very similar to one of the previous questions that we did. Given m equal to 128, n equal to 1024. So again, as a recap, n is this and m is this loop, right? And a total of 1024 threads being launched for the kernel. What is the total number of floating point operations? Again, you will count both additions and multiplications pertaining to the compute. So here the compute is the same pointwise multiplication. So the only difference is there is a loop up to m and you have an n also in place. So I will pause here since you have the options here. In case you need the previous slide, let me know. Okay, 256 cross 1024. Okay. Sure, let me just scroll up. Okay, so that 256 cross 1024 comes to B. Okay. Anyone else? Any other answers? Okay, 256 cross 1024. Let's take a look at the answer then. I think we waited for a good amount of time. Yes, it is B262144. So the explanation is n is 1024 and doing 128 times addition and 128 times multiplication for each I. Yeah, that is basically what this also gives you. One addition plus one multiplication, which is two floating point operations, and you have 1024 threads, and you have an M which is given to you as 128. So maybe this formula and the way the numbers are given to you are slightly, yeah, it should have been 1024 slash into 128 into 2, but that's okay, the product remains the same. I'll just correct that afterwards. So it is, or 256 into 1024 is another way to think of that. So the answer is B. I think this is also clear to everyone. I think we have one final question, so we'll move to that. Unless someone has doubts on this, I'll just pause here for a few seconds. Okay, if not, okay, again consider the following kernel snippet. This has line numbers, and I'll skip through this assignment line. If I less than n, you do a sine a of I. If I greater than equal to m and I less than n, you do a cos of that element. Else if I greater than equal to n, you do a sine plus cos. Right? This is your kernel snippet. So again, it takes two arrays A and B of size 1024 and performs the following operations. For the first 256 elements, you want to do sine A of AI. For the next 512 elements, you want to do cos. And for the last 256, you want to do sine plus cos. Right? But the values of m and n, these are arguments, right? So they are passed as 256 and 768, and the code has one line with a logical error with respect to this specification. So this is your specification, right? This 1, 2 and 3, this is what you're expected to do. But given that you are taking m as this and n as this, there is one line in code which has an error. So you are expected to find out that error and identify the line number corresponding to that error. So I'll just pay attention to this 1, 2 and 3 and the m and n, and then we can scroll back to the previous slide to see what the code is doing. Okay, I will move to the previous slide. So this is what you have. Any answers so far, or is this too confusing? Okay, someone has an answer saying 4. Okay, if it's very confusing, think of it as all you need to pay attention. It's a long question, I agree, but all you need to think of is if you were to write this, right? If you wanted to do this for 256, and then for the next 512 you want to do something, and for the last 256 you want to do something else, how would you structure these if else if, and again an else if statements. That's all you need to pay attention to. That's the key part of the question, and I think that doesn't even have anything to do with CUDA programming. It's just basic programming. Okay, someone has an explanation as well. Should be M, not M. Okay, in the interest of time, we'll actually look at the answer. Yeah, so that is the answer. Line number 4 should be if I less than M. So what do you want to do? For the first 256 elements, you want to compute sine of AI, and you're passing M and N as 256 and 768. But what you're doing here is up to 768 you're computing sine of AI, which is not what we want to do, right? The spec says for the first 256 elements we want to do this. So if it was M instead of N, then for the first 256 you would be computing the sine, and for the next 512, which is handled by this greater than 256 and less than 768, which is the sum of 512 and 256, right? So that takes care of the next 512 elements, and there you're doing cos, which is as expected. And then beyond that, beyond this 256 plus 512, beyond 768, you want to compute this part, right, which is again what is being done. So yeah, that's the answer. So basically this line number 4 which says I less than N is wrong. It has to be I less than M. That's about it. But it's a very roundabout way of asking this question. So I hope this is clear. I just have one last slide here. So I'm assuming by now you would have used the GPU since you have all your CUDA programming assignments, right? So is CUDA the only way to talk to a GPU or to write GPU programs, right? So the answers to that is it's not the only way to do it, although for a good number of years it has become kind of the industry standard and everybody talks about CUDA while using GPUs, but there are other languages that are used. For instance, OpenCL is very common for Intel GPUs, and ROCm is common for AMD GPUs. So there are other languages or programming frameworks by which you can do the same thing that you do with CUDA. And if you use a GPU as an end user, for instance, maybe you've run a PyTorch code, right? So you didn't even have to learn CUDA, right? PyTorch internally takes care of that for you. So there are different ways, different abstractions at which you can use a GPU. So that's just something to keep in mind. And if you're interested, you can look up more about OpenCL and ROCm and how they're different from CUDA. It's just something to be aware of, that even though you're studying CUDA programming and GPU architecture, it's not the only way to write GPU programs. And with that, I think I'm at the end of today's session. And since we are already past 2 minutes past 9, I'll just wait a minute more to see if anyone has questions. And if you have any questions, comments, feedback, please post it on chat. If you don't have any questions, thank you so much for joining and for interacting during the session. Look forward to seeing you next Monday. You feel free to drop off the call. I'll be there for another minute and then I'll wrap it up. Okay, if there are no questions, thank you for writing shader programs. I don't think so. that I think we briefly touched upon the graphics pipeline itself with the vertex shader and the fetcher and all of those things. I'm just trying to look at the course outline, but as far as I know, I don't think it touches upon that. Let me just quickly check. Yeah, I don't see that listed. I see a lot of warp scheduling and multi-dimensional data, OpenCL, then neural network training, inferencing. So I don't think it touches upon shader programs. Great. So thanks everyone. See you next week. And yeah, hope this was helpful. Great. Thank you.